Okay, so we'll start out today by reviewing some of the midterm questions that I used last year, just to give you an idea and to not surprise you too much of what is going on. And the way I'd like to do this is I'll ask the questions and we'll answer them together. And we'll see how we get. Okay, the first question was on selectors. Give at least 3 different ways to select the second rectangle in the following code. You can modify the HTML but not change the order or appearance of the elements. So you should select the second rectangle. How could you do that?
You could use a class.
Yes, you could use a class.
You could use an ID.
You could use an ID.
Or you could just say select SVG, select G, select the rectangle side.
How would you do that?
Well, you could say select SVG, stores in the variable.
So in D3 you mean the JavaScript?
Well, in D3 you could say D3.select, right? Parentheses SVG.
Yep.
And then you store that in the variable, and then you say SVG. I don't know the correct syntax.
Don't worry about the syntax.
Yeah, but I know you can pass it through the variable.
Yeah. Okay. Any other ideas how you could select the second red rectangle again?
You can do it like there's a way using like the less than or greater than sign to select something that's a child.
Parent selector, child, like the child selector, and let's say ancestor selector. There's 2 different ways. So a lot of students actually wrote JavaScript for this question. I just really wanted the CSS selectors, but I counted the JavaScript as correct too. So we got through the correct answer. So there's the ID, the class, then this direct parent-child relationship, or this relationship. So this would have been essentially the perfect answer. So here in this example, this is a very simple example where we have an SVG, select all rectangle, map data, and then set x to 0, y to AB, width to some certain, like based on the function, and then attributes, style, and so on. So the question here is, what is the role of A and B in the function calls when setting the width of the Y position? When setting the width of the Y position. Let's say when I'm setting the Y position.
A is your anonymous data function. Well, you're using an anonymous function, and A is sort of your reference variable for that anonymous function for the data.
Yeah.
And then B is your index.
Okay, and so which one am I using here really?
For for Y you're using the index, but for the width you're using your.
Why do I still have to have A here?
Because you have to have data to index, essentially, right?
It's because of the signature of the function. Data is the first element, and the index is the second element. So here, for example, I'm only using A. I wouldn't need B. What is the relationship of the first parameter of the A to the DOM? Anybody?
First parameter of A.
Of A, yeah.
Well, isn't A just the data that you're passing, that array 127?
Yeah. What's the relationship of the data to the DOM? Correct. So it is stored as part of the element that it is mapped to. So if you like look at the DOM element, you will find a field that maps the data in this element. So this is basically how D3 stores the data. That was what I was trying to get here. What would happen if the SVG on the select here, if this didn't exist?
Then that data would be put into the enter group.
Yes, but for this particular example, what would the result produce?
Nothing.
Nothing. Correct. How could we fix that?
You have to merge enter with this SVG.
Yeah, you basically have to do an enter first. So if we didn't have an SVG already here, we would have to do an enter first. So that would be the right answer here. So, then they also ask for the values of A. Ask for the values of A, B, of A and B in execution order, and that would be 127, 61, 256, and then the index from 0, 1, 2. Okay. Any questions about this? This is the kind of D3 question, right? I'm not going to ask about any specific functions. You should definitely know about what are scales, how do you map data, how do you enter, update, exit, how do you transition? Yep?
Are we allowed to cheat sheet?
No. The next question was about data type properties. So here I asked students to fill out this table. We have 3 different data types: ordinal, interval, ratio. Then the question was, give an example of each of these data types, and then fill in whether these operations are supported and whether 0 is arbitrary. So what is an example for ordinal data?
T-shirt size.
T-shirt size, correct. Other examples for ordinal data?
Car size.
Car size, yes. If you say like compact, medium, large.
Product ratings on Amazon.
Product ratings on Amazon, exactly. What is an example for interval data? I heard it varies. Temperature, yes. Any other interval data?
Great.
What's it?
Great.
Grade? Grade. I think like a letter grade would probably be ordinal, not interval.
Direction.
Altitude? Do you think altitude? What is the characteristic of an interval data scale?
Arbitrary 0.
Yeah, so we kind of have a meaningful 0, right? That's basically where the line starts. So altitude would be a good ratio example. So what are ratio examples? Speed, correct? Height. All of these things like length and duration and so on. And so, which of these operations are defined for ordinal?
Ordinal has equality or non-equality.
The first 4, yeah. So equality and checking for smaller or bigger. For interval?
Not multiplication or division.
All of them.
Not multiplication and division, but all others. So interval data, since we don't have an arbitrary series, it doesn't mean it's not necessary, like it's not meaningful to say it's twice as hot today as yesterday. And for ratio?
All of them.
Yep, for ratio, all of them are applicable. And 0 is arbitrary. For?
Interval.
Yeah. Okay, it's not arbitrary for ratio data.
Quick question.
Sure.
So when we say the weather is twice as hot today compared to yesterday, are we referring to the idea of like hot, cold, or are we referring to the actual temperature?
To the actual temperature. So if it's 20 degrees, or let's say if it's 70 degrees, it's not twice as hot as if it were 35 degrees. It just...
But wouldn't that be more of like a speech, like a language type of thing? Because like technically speaking, well, I see your point now. Like you're basically saying, when you say like it's 40 degrees, and let's say yesterday was 20 degrees, it's not necessarily actually twice as hot.
Yes. Because the 0 point is arbitrary. If I converted your temperatures to centigrade scale, which is another completely valid scale, this expression of twice as hot wouldn't be valid anymore.
Do you know if that holds true for the Kelvin temperature scale?
No. For the Kelvin temperature is absolute, but the Kelvin temperature scale is not very practical.
Okay.
But yeah,
So Kelvin is considered ratio?
Kelvin is considered a ratio because absolute 0 really means the absence of temperature in this case.
Thank you.
What about directional data, azimuth? It seems sort of gray because there is some relevant math on the ratio of one angle versus another, but 0 is arbitrary. 0 from 300 to 60. For example, 1 and 359 degrees are pretty close to each other.
I think it depends on the definition, and I really haven't thought about it. It depends a bit on what you're exactly trying to ask. So elevation. So what would be an example, like an angle, essentially, wind angle?
Yeah, there's a lot of things, just orientation of objects spatially by azimuth.
Yeah, that's a good question. I think basically what does it mean? The 0 is kind of arbitrary here. Like we have a convention of what we call 0, so I would say that's an interval scale somehow. But then if you can make sensible expressions about the size of the angles. So you can say 30 degrees is twice as wide as 15 degrees in this case, yeah. So it depends on what do you mean direction or relative size, I guess. So it's not an easy, not a clear fit, yeah. That's a good example. Okay. What is preattentive processing? Which properties are preattentive and how can it be used in visualization?
It's like the first thing you notice,
Yes.
or things that you noticed before.
Yeah. And so, maybe try this a little bit more formal.
It's things your brain notices before you apply focus to whatever you're looking at.
Yeah, that's a way of saying it. Anybody else has an interpretation? So what is it? What does distinguish a preattentive property from a non-preattentive property?
You don't need to serially search it.
Exactly. It's parallel search. You get an immediate grasp of all of the elements, how many there are, whether there is an element or not. So the example, what are properties that are preattentive? Color. So yeah, if we have color, for example, if we have all gray dots and one red, we immediately notice there's one red dot. If we have many different words and one word is different, then we don't immediately notice it, right? So if we cannot preattentively spot one specific word in the text. Color is a preattentive property. What are other preattentive properties? Shape. Length. Yep. Grouping. Yes. So these kinds of questions, I think we asked for 3 or so. And how can it be used in visualization?
Color highlighting.
Color highlighting.
Basically prioritize the data you want to convey.
Exactly. Yeah, so that would be a good answer for this question. Here are a couple of examples. Stephen's psychophysical power law describes the relationships between two things. What are they? Why is the law important for visualization?
Was it attention and sensation?
Not attention, no, but the sensation, yes.
Like physical intensity.
Exactly. Physical intensity versus perceived intensity. And why is that important for visualization?
You want to keep the ratio as close as possible.
Exactly. And what kind of different attributes did we look at, and how did they differ?
One is length, and this is the electric shock.
Exactly. I've seen the electric shock every time. So yeah, so we have these like length, area, depth, brightness, saturation, and so on. And so the power law is that the physical intensity is perceived to the physical. The sensation is the intensity to the power of n, and here n is from 0.5 to 3.5. So we have this non-linear relationship between physical intensity and perceived sensation for these different stimuli. And so we can see, like for brightness and depth and so on, we underestimate things, and for saturation and electric shock, we overestimate things. And only for length is it linear. This, yeah, that's basically what I said here. And then this is something that I mentioned last time. What is the degree of interest function? What is it used for? Evo's distance, yes.
API is a priori interest.
Correct. And the a priori interest. So this was essentially given a collection of objects. We have some that are inherently more important, and we have some that we currently are looking at. And so what we want to see, like what if we want to dynamically adopt the visualization and dynamically change the amount of content that we show, if we want to be smart about this, this is a way of doing it. So having, like, showing elements that are generally important is what the a priori function defines, and showing items that are close to my currently selected element y is what the d term defines. Yeah, is that clear? Good. And then this was the design critique. I'm probably gonna give like a little bit less theory questions and a little bit more design critique this time around. This one didn't have a redesign in it. So here, this shows, like this is everything that was on the assignment. So this picture, United States economic activity split in half. And then this map. So what do we see here? What's the data?
Is it saying that 50% of the GDP is in the orange areas and the rest is in the blue areas?
Exactly. And what does this chart try to communicate?
There's a lot of economic activity going on in those orange areas in comparison to the rest of them.
Correctly. And so, for example, Salt Lake City is not on this map. So what's the kind of implicit bias that this chart tries to communicate?
Only the orange matters.
Cities drive economic growth.
Yeah, only the orange matters. Cities are where it's really at. Any like ethical implications of this chart?
I think it's probably a little arbitrary because they had to make some choices of, well, we're at 49%, so which little dot are we going to pick for that extra one? And over on the East Coast, there's some really tiny specks that they grabbed, and there's a good chance that downtown Salt Lake actually had an equal amount of contribution to one of those little specks, and they could have said, oh yeah, Utah does it, but instead they wanted to focus out on the coast.
Yes.
So it's like how you define the boundaries.
Yeah. And so what is this chart actually showing?
Population densities.
Exactly. This is just showing population density. Of course, there's a bit of a difference in, like, the GDP per person in New York City is going to be higher than the GDP somewhere in Kansas per person, just because also the cost of living is higher and the kind of jobs that are available in these places is higher. So, do you think this is a fair depiction of, like, what basically? Okay, what's the? How could you phrase this? Like, what does the chart want to communicate if you want to be snide? If you just want to, like, provocate.
Screw the rest of the nation, man. You should be living in one of those orange spaces.
Exactly. So that's kind of the message, like the countryside, the flyover states, and so on. None of that matters. And so this was kind of like a hotly debated chart on Twitter and on Reddit. And So yeah, the problem here is, of course, that GDP isn't really, like, you can't say that like, for example, the blue, like if you color food production in the United States, how much of the food production happens across the United States instead of the GDP, then it would be pretty inverse, right? So you would see that in the countryside there's a lot more food production. So this kind of assumes like biases for GDP. It is kind of not a great chart. And so another problem with this chart is, of course, that it uses a map which and doesn't account for population, because it would be much more interesting to see this contribution to GDP if it were somehow normalized to the size of the population. So that's a general problem with maps, that they tend to most likely reflect the density of population and don't really tell us much if we plot it on the map. And so we'll talk about this more when we see maps. But so essentially you will get something like this. It's going to be some questions. It's kind of like an essay, more like, and you should, I'll probably give something that is a little bit better to justify with respect to the visual channels and everything that we learned in perception, where you should then make an argument, okay, this is not well encoded here, this is what you could use instead, and then design such an encoding instead. Okay, so this was kind of the slides. Any questions about the midterm?
What was the average?
The average? It was like, I curved it to a B plus average. And like the non-curved average was B. So like a lot of people got it right. Nobody basically got this one right. And then the degree of interest function, there was like 5% of people who got it right.
That was about the length of a full test?
No, I skipped a couple.
Okay.
So it's 50. This was 15 questions. I'm probably going to do a little less because it was really, really took me a long time to grade all of this. So I'm going to probably do 10 questions or so. Any other questions? Good. So then let's go back to interaction. So, like a quick recap from last time, we talked about interaction methods, like input devices and so on. Oh, by the way, so a couple of organizational things. Next Tuesday, by the way, so the scope of the test is everything that I will be talking about today. So Tuesday's content is going to be in the second midterm. And I'll put up the slides of everything that I've been talking about, so you have everything that you need for the midterm by tonight as slides. And then for the homework, I guess everybody saw that we will like push the deadline by a day, and Carolina moved her office, like added an extra office hour for tomorrow, but is doing 1 hour less today. So what was the time for tomorrow?
So today's the same time, just the first hour, 3:30 to 4:30, and then tomorrow is 10:30 a.m. to 11:30 a.m.
So if you need any help, this is the office hour. Is there any other office hours still, or are these the last 2 ones for this?
No, but on the topic of office hours, I do encourage people to post their questions and send me their script so that you're not stuck too long. Sometimes it's a small little thing. Email me your script. Don't email it to the ski address because apparently JavaScript, if it has a JavaScript attachment, I don't get it. So just you can do it through Canvas or you can do it through my Gmail. Both of those are. But send me your script if you're stuck on something. Sometimes it's very small, and if it's not office hours, there's no point in spending a whole day on it.
Good. Who's doing the hacker version? Raise your hands. 2 people? Well, 3, 4. Some not yet quite sure. Okay, good. Yeah, and then so we were basically going through different types of interactions. We had change over time, navigation, semantic zooming, filtering and querying, focusing context, and so we got stuck somewhere around semantic zooming, I think. And then we will also talk about views today, if I have the time, about multiple views, linking and brushing, adapting representations. And there will be more on filtering and querying. There's a specific lecture on filtering and querying right after the fall break. We talked about animated transitions. So the transitions can be super helpful if it's like a manageable amount of elements that you transition around. They kind of can help you keep your mental map. We looked at this study that did research on how to do animated transitions and whether they're good or not, and so they found that it is very helpful, but I also mentioned that they had a limited number of samples, not subjects, but elements and bars to track, so it gets a little bit more tricky with transitions when you have a lot of elements. For navigation, there's these three basic commands. There's pan, zoom, and rotate. And so we looked at this in the context of a 3D volume visualization here. We want to rotate, we want to be able to pan and zoom, and within those slices we could actually navigate through the slices. And we would see the relationship to these slices in the brain here. And so these are these space scale diagrams. It's essentially you define a viewing window, your screen, and then you navigate along these diagrams to pan and zoom. And then we talked a little bit about scrollytelling, that is kind of nice on one hand because it is fun to use and it can be usable, but it can has also some disadvantages. So you don't really have a way of discretely accessing specific states, and sometimes that's kind of an implementation question, but people can break the expected behavior. So basically the rule here is don't surprise people with what happens when you scroll. It should be kind of a natural thing. And so semantic zooming was another interaction method, and here the idea is that you have an abstraction that you present as an overview, and then when you zoom in on an individual detail, you see more of this. And so we saw this video where these are all CPU usage for different processes. And so this is, the CPUs are zoomed in a little bit, and so we see these spark lines here for the it's either just color or color plus spark lines, or completely zoomed in with labels and axes, depending on where you want to navigate, where you currently are with your navigation. So the idea of this is that it's readable, that you use visual encodings that are readable and sensible at multiple resolutions, so that you can somehow represent an item at multiple resolutions. Then we started talking about focusing context. And so focusing context is the synthesis of visual encoding and interaction. So here are these different approaches to focusing context. This is eliding data, superimposing data, or distorting the geometry, and we didn't get through that. So here's this example for elision. So on demand, you expand this dynamically. It's a classical example. You uncollapse a tree. And then the degree of interest function, I think we covered this today. And then for superimposition, we have a focus layer that is limited to a local region of view, and instead of stretching it across the entire view. So here is an example of superimposition, the magic lens. Magic lens is, there's different data shown depending on a lens definition. So let me show you this video because of also of historic interest.
Areas. Work areas in which information is displayed. Control panels containing buttons, menus, and other interactors. Our new interface reduces this effort by taking better advantage of three common skills: the ability to use two hands in concert, as when playing the piano, threading a needle, or typing. The ability to bring tools to hand, running the Cedar programming environment. The Smart Station is equipped with a mouse for the user's dominant hand and a trackball plus thumb wheel for the user's other hand. This region of the screen contains a simple window system that appears above application windows. We can move a sheet of tool glass in two ways, by dragging it with the mouse or with the trackball. Using both input devices, we can move a tool glass sheet and the mouse cursor simultaneously.
So, okay, this is not really what I wanted to get at, but this tool glass is essentially like you have this matrix of colors, and then you put the color that you want over the object, and then you click. But what I really wanted to get at is this magic lens.
To change the graphical style, we'll set the typeface of text, or can copy an opera into another one. Cup a shape. For example, tool glass sheets can include magic lenses, visual filters that modify the appearance of the objects beneath them. For example, this lens magnifies the objects underneath. We control the magnification with this slider, increasing or decreasing. This second lens is a filter that shows only red objects. Overlapping the two filters composes their effects. When we place the magnifier lens over the red object lens, we see that this little red object is a Time magazine. Magic lenses can be used to modify a scene's appearance in small regions, while leaving the rest of the scene alone as context. To move the Time magazine from the kitchen table to the nightstand in the bedroom, we can use two different magnifying lenses, one over the dining room table.
Okay, so the idea here is, and that is kind of used sometimes in, specifically, let me see what I have an example, yeah. In like volume renderings, for example, of the body, so that you have like one, the default picture shows the human, like a human head, for example, with all the skin, and then you have a lens where you can essentially remove the skin and then move that around. And so this is what this example here does. And that's even tangible.
In this video, the user interface and software engineering continues and takes up to now much pictures by performing multi-touch gestures on the table surface. In the following, we show how this task can be accomplished in a more natural way. For this purpose, we developed a paper-based mobile display that users can freely move through the physical space above the tabletop. This magic lens works as a magnifying glass to zoom in on an image by simply lifting or lowering the lens. At the same time, moving the display horizontally resolves a panning operation. In order to help users maintaining the context, a circular contour line is projected onto the table display.
Yeah, so how could you implement this?
Track the circle and then track the screen.
Yeah, so but what is the problem if you track this? Like, okay, what are the technology, the fundamental technology? So what are the things that you would use here?
I don't know the fundamental, but I'm pretty sure you can, for example, implement an OpenCV probably.
Yeah, no, I mean more like how is it displayed, the data, for example, the table. There's two ways of displaying data on the table, right? There's projection and there is like using a screen. In this case, it probably makes more sense to use a screen because then you don't have occlusion if you move about it.
Right.
But for the lens itself, you can actually use a projector, and you can actually use a camera projector setup to track where the lens is exactly, and then only project here, and everything else make it dark. You could also use an iPad, like simply do recognition of the position based on the camera of the iPad. So you could use an iPad, for example, as a magic lens, and people have done that.
Setup of our system is simple. The images on the lens display are generated by a projector and an infrared camera above the table. It works because the mobile lens contains markers in the corners that reflect infrared light. So the infrared camera above is able to track the lens movements. This tracking information is then fed to a computer which tells the projector what image to display on the lens. We have also applied the mobile lens concept to other types of information spaces. The layered information space is a set of two-dimensional data, with each data layer representing a unique feature of a contextual model. In our example, medical students can study different systems of the human body. By lifting or lowering the lens, they can choose between the skeletal, muscular, blood, and nervous system. At the same time, a single layer can be explored by moving the lens horizontally.
Okay, so this is not necessarily like tangible like interfaces for this is cool, but this doesn't have to be a tangible interface, right? You could use just like a lens that is completely virtual on your computer. There is also magic lenses that, for example, resolve edge overlap. So here, this is a flight path in and out of Toronto. And you can see that it's really hard to see the actual cities because all of these flight paths overlap with that. And so you could actually define this magic lens and then bend the curves around it. Or you could create a magic lens, for example, for a scatter plot. When you move it around it, then it labels all of the dots in a scatter plot. So that would be a pretty cool interaction technique. Like if you have like a rectangle that you move around and then get dynamic labeling for the elements in that rectangle. And that kind of avoids the problem, like if you try to label every single dot, you would get a lot of occlusions and you wouldn't be able to see the things in detail. Distortion is another way of doing focus in context. The geometric distortion, what we want to do with geometric distortion, we define a focus region and that is kind of increased in size, and the context region is decreased in size, and we have smooth geometric transitions between them. And so here, well, this is not smooth, but there's a geometric transition. This is a historical example. So we have a timeline. This is the perspective wall, one of the first information visualization papers done in Xerox PARC. And so what we have here are when different files types were generated and created. And so we have like a focus area here, and then we have two context areas that kind of use perspective 3D, a perspective 3D effect to show, okay, there's more elements back there and there's more bell elements back there. Do you think this is an efficient visual representation?
It distorts the time axis.
Distorts the time axis, yeah.
And as you slide the window farther to the right, it's going to be harder, it's going to distort the time axis even more to the right, such that eventually you won't be able to see it, right?
So I guess I would say this is partially effective, right? It basically gives you like an idea there's elements back there, and it seems like there's a big cluster of elements around here, so you can see that. You could say, okay, I just want to navigate to that if I want to resolve that in detail, but I could also just not use the 3D effect and simply compress this on this side. So the 3D effect doesn't really help much other than that it's easier to initially understand what is going on. So here's like these examples with a fisheye magnification. If you do this like on a regular grid, that's what a fisheye would look like. So here's a historical.
I select a rectangular region, then uniformly scale it. Notice how outside the handle, distortion falls off with distance from the selection. I can drag the handle around to focus on other regions. All of the nodes that fall entirely within the handle are uniformly scaled, preserving distances or
so notice that there's labels only when it's zoomed in.
Although the morphing function is not invertible, we can still allow editing. This is possible because
so this was kind of like a big deal in the hype in the 90s, and so here is an example of a hyperbolic tree.
It's context technique for browsing large hierarchies. Here we see a recent org chart at Xerox PARC containing over 300 nodes. The root of the tree is at the center of the circle, and successive levels of the tree are closer and closer to the edge of the circle. The edge is kind of like a vanishing point. Spacing gets smaller and smaller as nodes approach the edge, but the entire tree is displayed inside the circle. The structure of the tree is prominent, even when some nodes are too small to display text. For example, staff positions can be distinguished from line positions. By clicking on a node, we bring it into the focus area. Thus, we can see more of the detail in that part of the org chart, while maintaining the context of the whole. We can also grab a point in the space and drag it around as we like. To achieve crisp dragging and to keep transitions under 1 second, rendering of the tree is degraded in a couple of ways. Notice that the arcs are turned into straight lines and less of the exponential fringe is painted. The hyperbolic browser, like other focus plus context techniques, deals with the shortage of screen space by showing more about a few amidst a little about many. Here we use wafers to show the amount of space available for node information. Notice how nodes grow as they approach the center and shrink as they recede. We can interactively adjust how space is proportional, say perhaps to introduce a sort of spatial socialism. The hyperbolic browser can support other types of hierarchical data sets, e.g. part assemblies. For some applications, an alternative layout is QuickDoc.
Overview of the Xerox web server. For the Xerox homepage.
These things, they hint a little bit on the kind of research that was going on at Xerox PARC in the 90s, where it was really kind of the leading lab for user interface research. Here's another example on a map where we have a focus and context lens. Or here, this is like an example of exploring public transit bus stops.
It is possible to monitor the activity of buses throughout Singapore, but considering the large volume of information, exploring individual bus stops is a challenge for visualization. In order to achieve this, an interactive tool has been developed. It acts like a magnifying glass, allowing you to explore with great detail the activity of the bus network in Singapore. This magnifying glass distorts points in space to accommodate great zoom levels. It permits local browsing of the space, maintaining its continuity and emphasizing other distinctive points in the periphery. The lens can be dragged over the bus network of Singapore or focused on.
So, all of these techniques, they try to do, like, show something in detail and have the rest in context and only hint at it. So here's an example that I can also show live. So going back to this university ranking data set, this is like a big data set, so there's a couple of thousand universities in here, and so we can actually use this hyperbolic approach to navigate through this list. So we have an idea of like what is the size of the bars at the biggest universities while still being able to see like the details of the smaller universities. And at some point we kind of make a decision to not show that anymore. So you can dynamically zoom in here.
That's cool because it maintains the informative aspect of position.
Yes, it does, to some degree, of course. It is limited, so you can see that I don't see 4,000 elements here, right? Basically, like what I have is, I get to click here, I get about 100 elements on the screen in total, and so if I don't do that, I get about 40 elements on the screen. That's like, multiplied by 2, you could probably stretch that to fit in 3 times as much information. And this has been done, of course, for trees. The problem here with compared to, let's see, is this alive? Yeah. So what is the problem if I use this kind of approach on text compared to using it with what we saw earlier with the bars?
No matter, like, even if the bars are really, really small, you can still get some information out of it.
Yeah.
Not text.
The text is essentially not readable. So this video, my internet connection doesn't seem to be so great here. That's why the video doesn't play. But I guess you believe me that this works essentially like this. That you see the text zoomed in here. This is a pretty cool idea. It's called, like, who of you has read Calvin and Hobbes? And so Calvin had this transmogrifier, this box where he could step into and transmogrify himself into whatever he likes. And so this technique is called the transmogrifier. And so the idea here is to straighten complex shapes in image space. And then, for example, you could brush along a river and then get the river linearized and see where all of the other, like how what are branches of the tree and what the local context of the river is. So here, this is an example from major rivers across the world that were brushed on this world map. It can be spatial data, but they also show that they could, for example, straighten out a pie chart into a bar chart just in image space without knowing anything about the underlying technique. So that was a cool paper. I'm not so sure about the applicability, like about the value of it in like real data analysis, but it was like really nicely done. So like all of these techniques do some kind of distortion, and while this was pretty hip and in and looks great and has these wow effects, it has a couple of problems. So it's rather unsuitable for relative spatial judgment. So if you looked at the bus lines, like anything that is not straight in focus is really strongly distorted, and you kind of lose this medium context. Like the wider context is still there, but it's really hard to make these spatial judgments in close proximity to the lens. And it's also like mentally challenging to track how is this distorted, how does this affect the underlying geometry. So there is what you can do to help with grid lines and shading, so that there is some kind of guidelines of how a regular grid is distorted, and then you can try to read from it. But there's also this problem with the target acquisition. So if you have these lenses, picking the element that you really want to see in detail is sometimes not super easy. And so researchers have run studies on whether these distortion techniques are actually efficient. And so it's these studies have basically mixed results compared to separate views and temporal navigation. But in practice, they kind of like either you could say they have gone out of fashion, or we know better now. There's other and better ways of more like abstract aggregation instead of geometric aggregation. So like my personal guideline would be to, instead of using geometric like summaries or geometric distortion, use some kind of data-driven aggregation instead. I think it works okay for some cases, like for example for this for our bar charts, our stacked bar charts, but it's not so great, for example, for these bus lines. Okay, so next I would like to talk about filtering, which is also known as brushing and also known as selecting, and also about dynamic query. And so this is really one of the things that make interactive visualization fun and great. And so this, by the way, is Ben Schneiderman. He likes to post interesting pictures of himself on the internet. And so he is a famous author. He's probably, like, if you Google, like if you use Google Scholar to look for information visualization, he will be the first guy that comes up. He has runs a big research group in HCI at the University of Maryland. And so he kind of published this mantra of information visualization that's called overview first, zoom and filter, and then details on demand. So this is like a guiding principles of designing visualizations. So show an overview of all the data, zoom and filter in on something that you find interesting, and then provide details on demand. And so we'll talk about what that exactly means. There's also these other things that are important in information seeking, but for the purposes of this lecture, the overview first, zoom and filter, and details on demand are what is important. And of course, like any guideline, take this with a grain of salt. Like if I say don't use D3, I don't use 3D. I don't mean don't use D3 ever. I'm saying it again. Don't use 3D ever. I'm just saying use 3D if it really makes sense. And the same is true for this mantra here. There are situations, for example, overview first is sometimes not achievable. My counterexample is always, let's imagine you want to do a Google search. You wouldn't be helped by a visualization of the internet first. So there is limits to what you can do with overview first. So dynamic queries is also developed by Schneiderman. And so dynamic queries are, like you all know, database queries, right? You do select for something and then give some attributes, and then the database returns a query. And dynamic queries are exactly this kind of thing, but interactive. You specify the contents of these queries in a very interactive way. And so this is like a classical video.
Again, the principle is
This is actually Ben Schneiderman in the 90s.
visually demonstrate the query components and the results and provide rapid and immediate feedback. For that, I'll take a look at the demo here on this display. Just move over to the side here, and we see on it a map of the Washington, D.C. area with the Potomac here. And this is an improved version of where we were a year ago in terms of dynamic home finder. The scenario I present to you is that we're coming up on a new administration, and you've taken a job with the Clinton administration, and your spouse is going to be working at the University of Maryland. You're looking for a home. So the first thing to do is to mark where you want to work here at the University of Maryland, right about, let's say, there, the A marker. And then your spouse is going to work downtown in the executive office building, right about over there. There's the B marker. Okay. And now each of these points of light on the display represent a home for sale. And if I move to the right, I can control this display by choosing the distance that I want to be from point A. And now it's set at 30 miles, and I'm going to bring it down. And you can control rapidly, incrementally, and reversibly the distance that you wish to be from point A. So let's say you decide, you see there's plenty of them, so you say you want to be, let's say, 5 miles from work, so that you could, let's say, bike to work. And now you want to be somewhere inside that range from B, so you slide down, and we now can see the set. And this is, looks like we've got 40 or 50 homes over there. If I now choose about the number of bedrooms, I really want 3 or 4 bedrooms, so I move this double box slider to be 3 or 4. I've still got about 30 houses on the display, so why don't we look at the price now, and we want to keep the price down, let's say about 170,000, between 140 and 170,000. And that's given us a set of about a dozen here. We could trim a little further by choosing, we can choose from...
So I guess you get the gist. It's about dynamically defining those filters. And that's also like, it's also related to faceted search, like what you would do, for example, on Amazon. But on Amazon, it's usually not dynamic. It's like you pick a facet.
So it's particular to the example, I'm sure, but do you know if that is implemented as actual queries, or is it just a filter? It almost looked like it was just a mask, like an image mask.
So this is like there is many different ways to implement this, and the way I would implement it, it depends on whether it's a completely in-memory system or if you have a database in the backend, and then it depends on the size of the data. So for an in-memory system, I would basically just run a selection and then give an item a dot transparency value, or not render it at all, and I would treat it exactly the same as a highlight. So I would basically say it's either hidden or red or standard, something like that. For database queries, it's a little bit different. So, of course, if you want to show everything first, you already have to have it in memory. But then if it gets more complicated, if you use aggregation, then you could say, okay, I'm just going to give you an overview first with some kind of binning, and then once I filter, I go back in the database and retrieve more elements that match that specific query. So then I can get more complete results. But that is like an implementation choice, and yeah, so these examples here, I'm sure they do it all in memory. So here is a live example in D3 for this kind of interactive querying. So here we're looking at a parallel accordance plot, again, of this cars data set. We have the fuel efficiency, economy, the number of cylinders, displacement, horsepower, weight, acceleration, and the year it was built. And by doing this dynamic filtering here, like in this other case, if you look here, this was actually not direct manipulation, right? So we had these widgets on the side that there is like a disconnect between the elements that are drawn and the elements that are used to interact. This, in contrast, achieves the same thing with direct manipulation. I'm actually interacting directly in the visualization technique. And so now here I could also define this on multiple levels, as in this previous example. So you can see that well, let's be a little bit more generous. So now I can essentially say this has to be like a high MPG number and low displacement. And so I can basically do these AND combinations of these queries. Here are, this is an example of how to filter down this based on multiple geometric zooms. So we have an initial, super dense plot, and then there is a rectangular brush that essentially says, okay, only elements that go through that brush are of interest, and then they filter out the elements that are lower than the certain value here, and so you get these refined queries to look at these elements of interest here. This, of course, can also be done for volumetric data. So this is brain connectivity data, and here, for example, there's a definition: show me only the paths that are connected somehow to this brainstem. And then here, this is refined to showing all the paths that are both in the stem here, but that are also connected to these regions. So this is not restricted to 2D in any way. Another way of thinking about these filters is incremental text search. So if we have labels, for example, so we had this baby name wizard, and so there it dynamically updates based on, wrong field. So it dynamically updates with every change that I make. And that is kind of a neat interface because you don't have to type out the name, right, and you immediately see what is going on. And then you could also have more formal query interfaces. So this is an example from the set visualization technique that I showed last time. Again, the movies data set. So here we're looking again at the movies. But then I could now run a query and have an explicit query. It must, I'm interested in combinations of genres. The movies that I want to see must be an action movie, it must be a comedy, and it might not be a documentary, and it also shouldn't be a children's movie. And so here I have now essentially specified interactively within the interface with the same visual encodings a query, and I'm actually also showing the textual representation of the query to make it easy to discover for people. And then once I click that, I get this subset that matches that specific query. And so there's also a visual representation of that query. What would be nice here is, of course, if this were dynamically restricted somehow. Well, you see we have this bar, we see how many elements correspond to that intersection, but it would also be nice if we could dynamically see the result set here. Yeah, so then I'll talk more on filters after the fall break. Any questions about the interaction thing before I let you talk about tasks? Okay, so we have 20 minutes left, and I still owe you the lecture on tasks. This is short. This is short but important. Tasks is really what drives visualization design, which there is no visualization that solves every task. You always have to ask yourself the question, what are you using the visualization for? What do you want to achieve? And so if you want to design a visualization, you really have to understand what your end user, your potential end user, be it your customer, your collaborator, or yourself, if you want to do some kind of scientific analysis, what are the tasks that you want to solve with this problem. And so there's two classes of tasks. There's the domain and the abstract tasks. So basically there's an infinite number of domain tasks. But the idea is that you can take a domain task and break it down into simpler abstract tasks. And these abstract tasks, there's a finite number of things like, for example, I need to compare two data values. It's like one of these abstract tasks. And whenever you can break down a complex domain task to one of these abstract tasks, you already have a good understanding of which visualization techniques actually support these abstract tasks. So we basically, as visualization designers, we need to know how to address all of these abstract tasks, and we need to know how to translate domain-specific tasks into abstract tasks. And so if we identify the task and data combination, then there's probably already a solution for your problem. So let me just give you like an example for domain tasks would be to say identify the overlap or the correlation of gene expression between two different subgroups of patients. Something like this. So you have something very specific, very domain specific, and it is you have kind of like this this domain specific language in there. And what you would need to do is, as a visualization designer, you kind of need to break this down. So what you like, if you were to think about this, what I just said, you would come up with, okay, this person actually wants to compare two subsets of a data set. So we have this basic comparison tasks in there. And so there is these classifications of tasks according to Tamara Mansner. So there's these analyze, search, and query tasks. Analyze is about high-level choices. So these are kind of like higher-level tasks that are composed of lower-level tasks. And there's also a distinction between consuming and producing. So visualization is not only about displaying data, but you can actually also create data in visualization. For example, derived data, or for example, annotations. And then it's about searching, finding an unknown or a known item, or about querying. So for example, I don't know about the specific item, but I know about the characteristics that I'm interested in. So let me give you an example of some domain-specific tasks. So this is a university rankings data set. Again, so what we could ask is, find a good university with a high faculty-student ratio. And there's a couple of different ways that I could approach this. I could first identify high-ranked universities, and then in the subset, like this identify here is the lower-level task, compare universities and identify a high faculty and student ratio. Or I could derive a ranking with a high weight for faculty-student ratio and then look at that particular ranking. So these are two different approaches that I could take to solve the same domain task. Here is another example. For example, contrast Harvard's reputation scores with MIT's. And you could simply match up Harvard with Yale as a separate task. So what you would do is first find Harvard and Yale and then compare the two reputation scores. And then I could have a task, for example, find a combination of weights and parameters where Harvard is better than MIT. And then that's essentially producing a new data set by deriving it from input parameters. And so let's see if we can do something like this. So in this ranking, Harvard is higher ranked than MIT, and so I can dynamically adjust these. And I can essentially try to find a score, like one of these combinations where Harvard is doing better than MIT. And so the best way of doing this is simply to look at, okay, this wasn't good. International student ratio at Harvard isn't very good. So it's much better at MIT. And what is the faculty-student ratio? So we would need basically to identify one of these items where MIT is doing better. Is it possible?
Which is apparently pretty hard.
Oh, citations per faculty. So, okay, we found it. I'm now creating a ranking where citations is, of course, the most important measure, clearly. Yeah.
Can't be MIT.
Wow.
Or maybe the rating at the end.
So if you can figure out a way to do this, you might get a job at Harvard for representing the university.
So I think
those stars at the end are also contributing, right?
not in this case, no. So 99%. So it turns out to be almost basically. I can just remove the other elements.
There we go.
So here I kind of derived a new data set, right? And so I've not changed the underlying data, but I've changed our interpretation of it. And somehow earlier I found a simpler solution for this. But yeah, okay, basically I did the same thing. I removed the international student ratios. Okay, so let's go back and talk about these high-level actions. So there's these consume versus produce high-level actions. And so this classification by Tamara Mansner is on this consume side. We have this discover, present, and enjoy. So discover is really, this here is the distinction between exploratory data analysis and communication. If I want to present, like the New York Times does all the time, then my tasks are usually quite different than when I just want to look at a data set and try to understand what is going on. And the enjoy kind of falls a little bit into the category of our design study last time, where it's not so much about learning something specific, but about enjoying interacting with the visualization and discovering things. And then in the produce field, which is of course a little bit like less common in visualization, but it's still an important part, there's annotation, recording, and then deriving. And so you could dynamically derive data, as we have done just now, but data derivation from raw data is very often also a crucial design choice when you build a visualization. So how do you take the input data, how do you change it, adapt it, aggregate it, filter it, and so on, or calculate some differences so that you actually can communicate what you really want to communicate. So here is an example for annotation. Of course, this is this would really only apply if I were to dynamically annotate that. So if I could tell a story about any of those points. This is a derive example. So here we have essentially a distribution of elements, and what we do, we not only plot the raw data, but we derive some statistical values and use then those box plots to represent the mean, the quartiles, and still see the outliers. And so this was a snow chart that I used when we had this terrible snow in February of 2015 in Boston. So here's another example for data derivation. This is a simple list of football players, the clubs that they play at, the countries they're from, and where they are. And so just from this table, you could create something as complicated as that. But this is like a New York Times example. And it is pretty sophisticated, like what you can do just by deriving from such a simple data structure. You can essentially create like a big network. You can, by counting all of how many players are in these clubs, how many players that play in the World Cup are in these clubs. You can essentially, by deriving, you can see which are the major clubs in the world, and so you can see just in the overview here that the major clubs are Manchester, Real Madrid, Juventus, Chelsea, Barcelona, and so on. And so there's more to this chart. You can scrolly tell here and play with it, and then filter. For example, we could say only look at the North American players. In contrast to these high-level actions, we have these mid-level actions, which is about search and then also about low-level queries. So for search, there is always the question of what does the user know and whether the location is known. So we have, for example, target known, location known, then it's basically just a lookup. I need to identify an element, but I know what it is, where it is. If I don't know the target, but roughly know where I'm looking at, so I'm, for example, interested in the outliers in the scatter plot, then I would go for the browse task. If the location is unknown, but the target is known, it's kind of a locate task. I need to identify the element, where is it with respect to the rest of it. And if the location is unknown and the target is unknown, then it's more of an open exploration process. And then another important mid-level question is how much of the data really matters? Is it just about finding the one element and then learning something about this, then it's identify, or is it about comparing two different elements, as in this case, or is it about summarizing like a big set of elements? These are the major tasks or mid-level tasks that you should care about when you want to understand how much of the data matters. So here's a good example that has two things in them, that is compare and derive. So this is about the debt crisis, the recovery after the recession. So you see, this is like since this, so one thing that is nice here is it doesn't really explicitly show us the year, but it shows us the year since the first start of the crisis. And so what we can do here is we can actually map different crises on the same scale. Right? So here we have the Great Depression in 1929, and then we have the 3 different charts for different areas for the 2008 financial crisis. And so you can see that compared to the Great Depression in the United States, the 2008 crisis wasn't really a big deal, and this doesn't actually show the US 2008, well anyways. But in the Euro area, for example, the 2008 crisis wasn't a big deal compared to the crisis in the United States in 1929. Not so for Greece. So like Greece had the similar recession, the similar loss of productivity. And then this is now only for Greece, and so this is like a good example of instead of showing the data directly, showing a derivation. So it's not showing absolute GDP, but it's showing the change of GDP every year. And so you can see that essentially in these years GDP really dropped quite a lot. And see here there was like a brief increase in GDP, but then it went really bad, and then it's still like this GDP, like it was still a depression here, but at least the depression wasn't quite as bad, and then there is the first increase. So here like we see a comparison on the one side, and then also data derivation on the other side. And so let's talk a little bit about the targets. So if we want to see all data, we can try to spot trends, outliers, or features. And then if we want to see attributes, if it's only about one, we could look at the distribution, or we could look at the extremes. If we have many, we could look at correlation, similarity, or dependency. And for network data, there's a couple of different tasks, but roughly the most important ones are topology-based tasks and attribute-based tasks, which are not actually shown here. And then in networks, topology-based tasks are those that are concerned with the structure of the network, how is it connected, and paths are basically, if we want to see features, how they are connected to items or many items, for example. And attribute-based tasks consider attributes in the context of these networks. And for spatial data, we would like to see the shape. So here is an example for trend visualization and for outlier visualization. How did the job market develop since the recession overall? So here, like again, a scroll detailing interface, it says actually scroll. And so we can see these trends pretty neatly here in this visualization. We have these details on demand features, and we can also spot like the big trends. Like there's essentially we can spot the big trends that there are certain jobs that really went well in this time period, and then other jobs that really went bad. So for example, land subdivision or home builders, so anything that is related to the real estate market essentially really didn't recover within this time frame.
What is the x-axis?
The x-axis here is lower wages, higher wages industries. And so you can see that there is there's not a super strong trend between lower and higher wages industries. So, and then again, they use scroll detailing here to highlight individual outliers and major trends.
Oh, electronic shopping did pretty well.
Yeah. Okay, and so in the rest of this lecture, specifically when we, or not of this lecture, of the whole course, specifically when we start talking after the fall break about different visual encoding techniques, we'll be meeting many of those. So there's these different ways of achieving these tasks. So there's these encoding, manipulations, and we talked a bit about manipulations, these viewing attributes, about how fast it thinks, and then these reduction methods about filtering, aggregating, and so on. So like this is essentially like the symbolic overview of the second or third part of the course. Okay, so we would have 5 minutes left, but I'm not going to jump into views. So basically that concludes today's lectures. If you have any questions about your homeworks, I also have office hours. Like, do you have a question for the audience?
I have a question about the transactions or like interactions.
Yeah.
Some of these are not like intuitive for a user. So who decide what interaction like with the visualization? Is it the user or the designer?
Well, it's usually the designer should think about how to interact with the visualization. And some of them, as you say, are non-intuitive. Then if an interaction or like also a visual encoding is non-intuitive, you have to think about, is it worth it? For example, for an expert user. Like there are certain kind of techniques that are not intuitive initially, but that have great value once you've understood them, right? And so that depends then again on your audience and on your scenario. Like, do you want, like, are you a newspaper publisher and you need everybody to understand this at the first glance, or do you create a scientific visualization tool where you can expect people to have some training or invest some energy into using the tool? So this is the trade-off. But the decision on how to interact with it should be made by you, by the designer. Any other questions? Okay, so then we'll see each other on Tuesday for Sean's lecture on the design process, and then on Thursday, the midterm. Is it like one simple instance where it's too big? Okay, I'll sit down. I will be back. I'll have to look into it a little bit more to understand what's going on exactly. Yeah, but you don't have to worry about it. When you were talking